Please welcome to the S4 main stage, Reed Whiteman.
Hello. Can you guys hear me? I have the dubious honor of following the general. I wonder if this thing's been bugged. So my name's Reed. I will be talking about the easy button today. So my alternate title for this talk was called Bad Vibrations, and the reason for that will become obvious quite quickly, I hope. So a long time ago, at least by computer standards, which was back in 2004, there was this security focus article, which features Eric Byers, who I think is attending the conference this year. And it basically discussed how insecure programmable logic controllers were. And so, you know, the pull quotes here are that script kiddies could write attacks to go after PLCs. So the reason for that, of course, is that PLCs are mostly insecure by design. We didn't call it that back then, but you know, insecure by design basically means that there are unauthenticated protocols used for configuring the logic controllers. There are bad parsers in the logic controllers, which result in crashes, you know, all kinds of problems. So basically, anybody who can speak an industrial protocol can cause all kinds of havoc with the controllers. So sort of an epic battle started between the people who came from an engineering background and started entering the security space, and people in the security space that started entering the engineering world. And full disclosure, I'm part of this latter group. You know, I have no formal engineering background. I'm a security person who's kind of jumped into the wonderful world of engineering. So people like me, we look at PLCs and we say, all right, there are like parsing problems, there are backdoors, these things need to be fixed, right? I can upload ladder logic to this PLC and change how a process works. And of course, the real engineers say, yeah, but you know, show me how you're actually going to exploit the PLC to cause damage, and then we'll talk, because you don't know what the outputs of the logic controller are actually connected to. You know, you need to have a good understanding of physics. You need to understand the recipe for what the process is actually controlling in order to launch an attack against an embedded device that will have some meaningful impact. So my approach is usually like, you know, let's go shotgun hunting and see what we can find that maybe these criteria that the engineers rightly criticize the security quote-unquote engineers for, let's see if we can find some controllers that maybe satisfy those requirements where we can cause damage without a lot of detailed process knowledge. And one of the things that popped out to me right away were these variable frequency drives, also known as frequency converters. So you're probably thinking now, like, where have I heard about frequency converters before? Right. So anybody here playing bingo? Stuxnet. All right. So you get your free space on the bingo card or whatever. Stuxnet, of course, required people with giant brains to pull off. So I don't have a giant brain. But one thing that I noticed in these frequency drives is that a lot of them are controllable via protocols, and a lot of them have a critical speed setting, which is in the form of usually a skip frequency or a skip band. So critical speed has nothing to do with going 88 miles per hour. It actually has to do with rotating shafts, right? Any rotating piece of equipment has a drive shaft, and that shaft will begin to oscillate and vibrate and cause bad vibrations at a certain RPM speed. And the speed that happens at depends on the materials that are used in the shaft and all kinds of engineering principles that I don't fully understand. But the idea is that if you run the shaft at a certain RPM range, it will begin to vibrate, and it can cause damage to not only a motor, but to surrounding equipment. So this is kind of an example of, you know, a rotating shaft and its RPM band, and the y-axis here is the amount of vibration seen in the equipment, and the x-axis is the RPM. So it has a peak vibration level, and once you go through that peak vibration level, vibrations settle down, and then usually there's some kind of harmonic that happens later in the RPM range. So variable frequency drives have this protection setting, and that's this skip frequency, which prevents you from running the drive at the critical speed. Of course, the protection setting is really there for operators, right? It doesn't let operators set the variable frequency drive to run the motor at that skip frequency. But that skip frequency is part of usually the protocol map. So if it's a Modbus device, this is the Schneider Electric Altivar 12 device, that skip frequency will be encoded inside of the Modbus map. So VFDs don't really protect because that skip frequency there is readable and writable. And by the way, that R/W in that setting means that you can write that setting while the drive is running. Think about that for a minute. So VFDs don't actually protect anything, right? They actually give attackers a recipe for breaking your controller. So I say let's stop pretending that, all controllers are going to be these beautiful, unique snowflakes that are impossible for people to understand, that they'll need detailed knowledge of your process. Let's acknowledge that some of these things actually provide the recipe as part of their programmable map. They give you the recipe for doing the controller. So manufacturers, of course, differ, right? Every manufacturer that makes frequency drives has a different protocol map. So, instead of one recipe, we might need a few dozen in order to cover 80 to 90% of the frequency drive space. But, the recipe is mostly the same no matter what you're looking at. The steps are read that skip speed out because it's readable and writable, change that skip speed or skip band to be some range that's nowhere near what the old one was, and then set the target speed of the drive to what was the skip speed. So now the drive will begin vibrating. So then the question becomes, what happens when you start doing this to a motor? Well, there's not a whole lot of literature about it, but we did find one decent paper. We ran some experiments on a small 1.5 horsepower motor because it's all we could fit in the office. At face value, not a whole lot happens to it, right? We can see, we actually connected it to an external drive shaft, and we can see the shaft vibrating. Not a whole lot happens, right? There's no explosion. It's not like the second coming or something like that. But if you're using shaft couplers to hold that shaft to your motor, make sure you tighten them and use Loctite, because I didn't do that. And I ran it overnight one night, came into work the following morning, kept running it, and then the drive shaft fell off my motor. But yeah, these shaft couplers are pretty neat, but definitely use Loctite. The good read that I recommend is this paper from an engineering company in South Africa, actually. And they went and responded to a mining operation in South Africa where the mining operation was having problems with its fairly large electric motors failing. These were like 1 megawatt electric motors used for water pumps. So this is a pull quote from their paper, from the introduction. Basically, these motors at this mining operation were failing, and they were failing at a rate where the mining operation could barely get one motor repaired before the next motor would fail. The repair companies that the mining operation had hired were trying to figure out what was going wrong with the motors and were unable to determine what happened. This engineering company finally came in and figured out that the engineers at the mining company miscalculated the critical speed of their drive and were running their drives fairly close to their main drive shaft critical speed. So they ran their drives at their critical speed by mistake. This wasn't an attacker, this was just a mistake. And there aren't very many engineering papers where people run big electric motors at their critical speed for prolonged periods. This was just one that, it's kind of fortunate that this happened. And in fact, if you Google search for critical speed, electric drive, I think this paper might be the first one that comes up. But one of the notable things, too, was that not only was the motor that was being driven at its critical speed damaged, but the surrounding motors, which were left or turned off, were damaged from the vibration. They don't go into a lot of detail in the paper about how the motors were placed near each other, what kind of framing they were using to hold these things, but it was kind of interesting to see that surrounding equipment was also damaged by the motor vibrating. So it was bad vibrations. So why wasn't it caught, right? You think, all right, this motor is shaking violently or something is happening. Like, why wasn't the mining operation picking up on it? And from talking to a few people in the space about it, it turns out diagnosing vibration issues can be a bit difficult, right? It takes people specialize in this, real engineers specialize in this area, and diagnosis is hard, right? Because if you're an owner and your motors start failing, you probably think, oh, well, okay, manufacturing defect, maybe you call in a repair company or you call in the manufacturer to get the motor fixed. The second time, maybe now you're more dubious of the manufacturer. You think that they might have made a bad motor. Maybe the repair company you hired didn't do a great job the last time. The third time, maybe you try a new repair company, right, thinking that, both the manufacturer and the repair company stink, right? You're going through some troubleshooting process. Finally, you break down and you say, I'm going to hire some real outside engineers, some engineering consultants, and see if I can figure out, what is going wrong with our motors. So the diagnosis will usually require installing vibration sensors, temperature sensors, rerunning the math to make sure that you calculated the critical speed of your drive shaft correctly. And I talked to a local company. I live in the city of Indianapolis now, which actually has some engineering companies in it. This company called Datus, they specialize in instrumenting motors with vibration and temperature sensors. They tell me about 85% of all motors lack any kind of sensor at all. Of course, they're probably a little bit biased because they're selling these things. They have to be a bit optimistic about their future market space. But basically, all of these people have complete reliance on the variable frequency drive for detecting problems with their motor, right? Because they have no outside instrumentation. All they have is the information you can get from the drive itself. So, will critical stuff be vulnerable to this issue? I hope not. Probably not. I would like to think that hopefully anything that's running, a water pump at a nuclear power plant would have vibration sensors installed on it to ensure that it has a nice operational life and that, problems with it will be caught quite quickly. Hopefully they're doing the vibration monitoring. Hopefully that vibration monitoring is being done out of band with the actual control for the drive. And hopefully they're doing vibration monitoring on nearby equipment and not just on the drive itself. But that's a question that I don't know the answer to. So I guess the next thing that I think about in my list of self-complaints is, you're changing the motor speed, right? Isn't somebody going to notice that you're changing the motor speed? And, the kind of rationalization I give to myself how this attack might still work is, depends on how people monitor, really, if they monitor things like drive speed. One way to do it might be to run the Modbus VCR, which is a tool we released a few years ago for recording and replaying process state. So that's a really dumb way of doing it. Another way might be to look at Jason Larson's research with making more realistic, noisy, jittery-looking fake data out of a process control system. Another method that I was thinking about was a kind of a sneak attack using a very similar trick to the easy button. Sorry, there's a tiny bit of math coming up. So variable frequency drives calculate the RPM speed of the motor that they're driving. And they do that so that you can present that speed in RPMs on an HMI screen or something. The RPM speed is this really basic math, which is they take the nominal RPMs of the motor, which is the case speed here. They take the nominal frequency of the motor, which is usually 50 or 60 hertz, depending on which country you're buying it in. You divide RPMs by hertz, multiply by the output frequency that the frequency converter is putting out right now, and that will give you the current speed in RPMs that the motor is running. So if somebody sets a set point for the motor, the VFD would do this math automatically to figure out what frequency it has to run at to match that set point. But of course, the frequency drives all have this nice readable and writable setting for the nominal case speed and case frequency. In the case of the Altivar, at least, the R/WS means you can only write to this setting while the motor is stopped. You can't do it while it's running, thank goodness. But it's still readable and writable with no authentication. So the case speed in this case, you can set that in this particular frequency controller from 0 to 24,000 RPMs. You can set the case frequency from 10 to 400 hertz. So the attacker now, he doesn't need a big brain, just a medium-sized brain, and he can do the math and say, well, if I raise the case RPM setting, so I raise that case speed RPMs, right, the motor is actually going to drop the output frequency in order to keep the same current speed, right? So effectively, you're causing the motor to slow down, but the operator thinks it's running at the same speed. And likewise, if you raise the case frequency, which is the divisor here, the motor, the variable frequency drive will increase the output frequency in order to maintain the current speed. So you can kind of trick operators into thinking that they're running their motor at the right speed just by changing these settings. And these settings, the question becomes then, is anybody logging these settings, right? Because it's normally something that you set once in a frequency drive and never change. So are you storing this in your historian data? Or are you logging it somewhere? If it changes, will you notice, is the question. So I guess the lessons to owners here are don't just monitor RPMs from a frequency drive, do monitor your output frequency as well. But of course, none of the drives we looked at support any kind of data integrity. So, don't trust the RPM reading. I guess, don't control your frequency drives via protocols. A lot of frequency drives have the ability to run via analog output, which then you would have to use maybe a PLC to control the frequency drive. Of course, you could install firewalls. If anybody's still playing bingo, I said another F word. So who's vulnerable? All right, so I've been picking on Schneider a bit during this talk, and I'm sorry. They actually made the cheapest frequency drive that I could buy brand new. So that's the reason I went with them. And it's a nice drive. I mean, I don't want to fault them for that poor decision. So first of all, some definitions, because we like to have our little Basecamp style definitions. So a red X means that there's inadequate protection, right? So there's either no authentication on the frequency drive for changing these critical settings, or there's some kind of bypassable authentication. So that's the end of the definitions. You don't need any more. So ABB makes a line of frequency drives called the ICS 500 series. They fail, obviously. They have a Modbus. They actually have a few different skip ranges that they define, and they're all readable and writable by Modbus, at least according to the documentation. Allen Bradley makes a whole lot of variable frequency drives that go by the name PowerFlex. They also fail. They kind of get a special mention, though, because they try. So a lot of their small variable frequency drives that speak protocols like Ethernet IP fail outright. They don't have any password protection. Their medium voltage drives, though, which go all the way up to 34,000 horsepower, which is a fairly large electric motor, they have this protection. It's a 4-digit PIN code that you can use to protect the settings in the controller. And unfortunately, they made the decision to make this 4-digit PIN code readable, but they encode the 4-digit PIN. In case you forgot it, you can read an encoded form of the PIN, call the factory, and they will tell you what your 4-digit PIN is. So that probably means they're doing some kind of XOR, bit shifting, horrible encryption. So I think they fail. Schneider Electric, of course, I've been mentioning their Modbus map, and we've tested their frequency drive. They also fail. Vacon makes a line of frequency drives called the X4 series, which have plug-in cards for speaking different protocols, which also fail. So, takeaways. There's the easy button, right? It takes a bit of time for this easy button to do damage, but it's also pretty hard to diagnose. I think frequency drives are probably not going to be alone in this area. I think it's more of an easy button than the easy button. I think that the kind of formula here is there are devices that do both control and protection. And if you rely on the same device for both control and protection, you're probably lining yourself up for failure. So sometimes, an attacker might have to do a little bit of math to make the attack work really well, but in the end, they can make a program that's repeatable, scriptable. Along those lines, we did this thing called Project Basecamp a few years ago where we released some exploit tools. So Metasploit modules, just kidding. We're not going to be releasing Metasploit modules, but really it only takes like 5 lines of code in Metasploit to pull off this attack against like a normal Modbus frequency drive.